Hi, everyone. My name is Anthony Annunziata, and I'm the director of the IBM Quantum Network. In the last few years, quantum computing has advanced rapidly. The growth of this conference is actually a really good sign of the fast-growing interest from industry. In my talk today, I'll present IBM's vision for how we'll scale quantum technology and enable our partners through the IBM Quantum Network. IBM's quantum program is built on three pillars. At the foundation, we're striving to advance the science and the systems that will enable progress. This includes our hardware roadmap to 1,000 plus qubits, and includes our quantum theory efforts to harness the capability of near-term systems and chart the course to fault-tolerant quantum computing. We are taking these advancements and creating a cloud platform with the tools to enable developers to harness the capability of quantum systems. That includes tools for researchers working at a pretty low level, close to the hardware, as well as application-focused research and developers. And those are seeking to use quantum computing as a tool to solve practical problems and integrate with their existing IT infrastructure. Now, based on our systems and science and our platform efforts, we've created the largest client and partner enablement program. And it really is a global community with leading industry companies who are pioneers in their domain. It has startups, their universities, and their government research organizations worldwide. This community helps us advance our research and development, and it also helps us progress rapidly toward deployment of the first applications of quantum. Now, at the outset of my talk here, I'd like to focus on two essential concepts. The first, the quantum bit, needs no introduction in this crowd, I think. It's the information carrier in quantum computing, and it harnesses the properties of superposition, entanglement, and interference. The second, though, the quantum circuit, it's a little bit less famous, but it's actually more important. A quantum circuit is a sequence of quantum gate operations that form essentially the primitive elements of a quantum algorithm. It's the fundamental unit of quantum computation. Harnessing quantum computers to perform useful tasks relies on our ability to utilize quantum circuits. Quantum circuits that are essentially, they're classically very difficult to simulate, but they can be used in quantum algorithms for practical applications. Now, today, I'll focus on three interwoven stories at IBM. Stories about how we plan to scale quantum to achieve the great promise that we all look forward to. I'll start with our roadmap for quantum hardware. Then I'll tell you about the platform we're building to leverage this hardware and give developers the tools they need for applications. And then, toward the end, I'll highlight how we're engaging the world at scale to help advance this progress. We recently unveiled our roadmap for quantum technology development in the coming years. We're planning to deliver rapid advancements in the scale and in the capability of the hardware. We plan to more than double each year. By 2023, we'll have a system of over 1,000 qubits, and that'll mark an important inflection point in the ability of the hardware to run algorithms at increasing scale and level of error tolerance. Now, the members of the IBM Q Network will have access to the most advanced hardware based on this roadmap. But let's take a closer look at what's coming. Today, we have our user community using a fleet of systems with up to 65 qubits. We call this generation of systems the Hummingbird family. The key innovations that we've demonstrated with Hummingbird are high-fidelity readout multiplexing and also low-latency signal processing, which is for high-fidelity control. Importantly, we've maintained the reduction in crosstalk that we observed in the Falcon generation of heavy hexagonal lattice-structured devices. Now, in less than a year, we'll have our next generation of system online. We call this generation Eagle. Eagle systems will demonstrate a number of essential advancements that are needed to scale, including much improved mitigation of spurious modes, the incorporation of through-silicon vias, and high-fidelity multi-level wiring for improved qubit addressability and control. Now, if we look ahead to 2023, things really start to heat up. This is when the Condor generation of systems hits the scene. Breaking past 1,000 qubits may seem like a symbolic number, and it is, but it's actually much more than that. With Condor and the reduced error rates we're targeting, we expect to start a new family of systems that mark the beginning of an inflection point. Now, let me explain a little bit more about that. For the past few years, we have been benchmarking progress in quantum systems using quantum volume. Quantum volume will continue to be an important metric for some time. As we approach 2023, 1,000 plus qubits, and the much reduced error rates of Condor, we will see the start of a transition from purely physical error scaling, where quantum volume is a good benchmark, to software-based or encoded error scaling. Now, this inflection point is really an important step toward much more capable and eventually fault-tolerant quantum systems. With this hardware development plan as our foundation, I want to now switch gears to focus on IBM's vision and efforts to build a quantum cloud computing platform for developers that's based on this hardware roadmap. Now, a key concept to understand is that any form of quantum computing will entail coupling between quantum systems and classical computing systems. The key to building a practical platform for application development and for deployment is to deeply couple this quantum and classical capability. And the idea is that we use classical systems to control quantum systems, as well as to run algorithms and higher level workflows that utilize both quantum and classical capabilities. Of course, we need to make this easy to use and intuitive for developers. Now, it's not actually that hard to abstract away the physics, and I'm sure you've heard a lot about the various efforts to do this. But what is a bit more difficult is to create a platform that performs this abstraction, which is super important, but does it while making or maintaining the full capability of quantum hardware and making that available to developers. We call this abstraction without trivialization. Don't trivialize the quantum. That's what a bit does. It forces a quantum system to take binary form only. If you trivialize that, if you abstract it away, then you won't have the benefits of quantum computing. Now let's go one level deeper here. As we look at this deep coupling and what's necessary between quantum and classical systems, we actually see two timescales at play. One that we call real time. Now that refers to classical operations, classical computing operations that you can perform within the coherence time of a qubit or of qubit hardware. That's important for extracting the most capability from quantum systems. You need to be able to use some classical control within the time and responsive to what the quantum algorithm is doing. Now that includes eventually for performing error correction, but in the near term there are lots of other useful things as well that we want to do with real-time control. Now we're creating this runtime environment, real-time runtime, in our platform to enable quantum researchers to work at this level, which is what's required to extract the most from quantum hardware. Now, then there's what we refer to as the near time. That's another runtime environment we're building for developers, and it's intended more for application-oriented work. In the near term, it will enable optimal performance, much higher performance, for the various flavors of variational algorithms that are in use today. Now, ultimately, our goal is to create a quantum computing platform that contains libraries of optimized quantum circuits that form the building blocks of algorithms. Alongside this, we actually borrow an idea of traditional software development and apply it to quantum. That idea is the idea of a pattern library. Pattern libraries that describe known combinations of quantum circuits that are useful for specific things, specific tasks. We already have the initial versions of these libraries available, and in the coming years, as our hardware scales, we're going to scale the size and capability of circuit and pattern libraries so that we can address practical applications. Ultimately, our goal is to make circuits and algorithms accessible to non-experts by allowing application developers of today that are not experts in quantum and in physics to describe their problem rather than the solution methodology. The challenge of scaling this platform is to make quantum development frictionless, to infuse it in the software, in the languages, in the ways of working and workflows that developers of applications use today. Now, as we advance along our quantum hardware roadmap in the coming years, we scale out libraries of circuits and patterns, Our vision is to be able to run workloads on a quantum computer with just a few simple lines of code, like you see here, and knowledge not of quantum physics, but purely of the problems to be solved. Now, quantum technology is clearly advancing rapidly, and IBM is really committed to scaling hardware and our user platform. But the history of new technology development and adoption shows us pretty clearly that a single company, a single effort can't do it alone. So to address this challenge a few years ago, we created the IBM Quantum Network. Our partners join with us in the Q Network for many reasons. But among those reasons, perhaps kind of the most important is because the world is full of hard problems that matter to all of us. Computing as we know it with ones and zeros has taken us very far, as we can see all over the place, but actually not far enough. I mean, a quantum approach to computing promises essentially to unshackle us from the binary world of classical computing and open up the full promise of the science of information. Now, that's why this community is formed and why it's grown so rapidly, I believe. We created the network with a threefold mission. The first is, the broadest part of the mission, is to educate and enable people and organizations to help them get started on their journey to quantum. The second part of the mission is to advance quantum research. We focus on supporting and collaborating with organizations in order to advance the state of quantum science and to accelerate fundamental breakthroughs in theory, hardware, and algorithms and software that we really need to utilize quantum and to scale the hardware and to scale the platform. The third component of our mission is to collaborate deeply with industry, with the goal of launching the first commercial applications as soon as possible. We believe that quantum applications can most quickly be developed by combining quantum expertise with the expertise that leading industry partners bring in specific application areas, including chemistry, materials, finance, manufacturing, logistics, and others. Now, IBM was the first company to offer access to a quantum computer on the cloud. Since launching this access just over 4 years ago, we've seen really incredible growth of the community. Today, we have over 250,000 users, and they've, over the last few years, collectively run over 500 billion circuit executions on our systems. We've made 29 quantum computers available to those users, and the Q Network today includes more than 130 organizations, and it's growing rapidly. Our collaborators are working with us on over 30 important application areas that will form the basis for practical use of quantum systems over the next decade. Now, the fruits of this have already been seen in well over 400 research papers from our network partners and from our broader community. Today, in total, we have 135 members of the network collaborating with us to bring this vision of quantum computing to reality. Now, they include some of the largest and most influential companies in the world. They include leading universities, and they include engagements with governments, startups, integrators, suppliers, and others. Now here I'm highlighting the industry partners that have joined us in 2020. As you can see, these are leading companies across multiple domains, but they're united by seeing the promise of quantum computing to transform their business. With this select set of industry partners, the IBM team is deeply collaborating with teams from the clients. And the goal in this deep collaboration is to advance research, development, and commercialization of applications that matter to these clients. Here I'm highlighting a few examples of these collaborations. We're working with Daimler, and have been for a few years now, on several use cases, including in optimizing manufacturing processes, discovery of new materials, and in optimizing the product experience. With JP Morgan, we've been working on applications in finance, including especially in risk analysis and in derivatives pricing. We work with Mitsubishi Chemical on exploring materials and processes with the goal of increasing the energy storage density of lithium-air batteries. We've been working with ExxonMobil on building what is essentially a new toolbox for computational chemistry. And that would be something that their researchers throughout the company can utilize. We work with Delta to understand the use cases for quantum computing, and the focus there is on enhancing their customer experience across the day of travel. Now finally, we work with Boeing. We've actually recently begun a collaboration, and that is looking at multiple use cases, generally in the aerospace industry, and I'm sure you'll hear more about the details there in the months ahead. Now, I'd like to take just a closer look at one collaboration, the one with ExxonMobil, because I think it's illustrative of the way we work with a select set of partners. For 2 years now, our IBM team and the ExxonMobil team have worked pretty closely together, really hand in hand. And the goal here has been to advance the science and the practical applications focused on areas that ExxonMobil cares about. Now, a key focus here has been to enhance the accuracy of quantum simulation for chemistry, as I mentioned, to create this new toolbox for computational chemists. Now, this is a snapshot of the team here on the slide on the bottom working together. And in the upper right is a snapshot of a recent paper the team published. Now, this is an example of the type of work that we do together, and it's an example of the output that a deep engagement can create. Here are some foundational work to advance the accuracy of quantum algorithms in chemistry. Now, for the last few minutes, I'd like to switch gears and tell you about a different type of partner, one with a startup. Now, this is Cambridge Quantum Computing. IBM has continued to deepen its relationship with CQC over the past 3 years, and that's included integrating their TKIT compiler with QuizKit, doing joint work on benchmarking. We created a partnership with CQC that utilizes access to IBM's quantum systems with their clients as well. And recently, we unveiled the first joint offering between IBM Quantum and CQC. It's about something that we can easily overlook, but it's actually really important to business and science. It's random numbers. Reliable and trusted generation of random numbers is actually not a straightforward task. There are a lot of methods, but those methods use only typically pseudo-random numbers. They generate only pseudo-random numbers. Or they rely on physical phenomena that appear random, but they're not demonstrably random. We just think they are. They look random. Now, quantum physics is special because it exhibits true randomness. A qubit in superposition, it doesn't have a definite state. Each time you measure it, you can't definitively predict whether it'll be a 1 or a 0. You can only make a statistical statement on probability, which becomes testable after a large number of trials. We call those shots. Now, that means, in theory at least, a quantum computer can be used as a source of random numbers. Importantly, a quantum computer also provides a way to test whether the source of random numbers is quantum, and by extension, whether they're likely to be random. Now, that's a Bell test, or a specific version of a Bell test called a Mermin test, that we can use to show that a system exhibits entanglement, which is a property only present if the system is quantum. So utilizing this collaboration, this algorithm from Cambridge Quantum Computing, we developed an approach on IBM's quantum systems and recently made available, to our knowledge, the first cloud-based quantum random number generation service with an integrated Mermin test that can use to verify the randomness. And we offer that through QuizKit, through the module QuizKit_RNG. Now, this is something that I really believe is a great example of taking a new scientific result, harnessing the capability of quantum hardware, doing it in deep collaboration with a partner, and then offering it to users through our platform. I think it's a really exciting step toward making quantum computers practical and useful, and I'm really looking forward to see what scientists and developers can create using the service. Now, in closing, I'd like to express my excitement and the excitement of the entire IBM team for the road ahead. IBM is working really hard to scale the hardware and the practical user platform. We're working hard to enable a broad ecosystem of partners. Now, if you're in the audience today and contemplating what to do about quantum computing, my message to you is that it's time to act. Don't stay on the sidelines any longer. Quantum holds really a truly gigantic opportunity for business in the years ahead, but its benefits will only go to those who understand how it will be used, how it will be adopted. In essence, it will go to those who engage early to get a head start. So I invite you to be part of this journey. Thank you for your time today, and have a great day. Enjoy the rest of the conference. Thank you.